Welcome to the lecture for 9.7, where we are going to approximate we're going to approximate some elementary functions with polynomials. So I want to start with an example of something that we've done before, which is doing a tangent line at a point. And another way that we're going to call this is just a first-degree polynomial approximation. Of the function given f of x. So a first-degree polynomial, by the way, is just a naught plus a1 times x. So this would be a first-degree polynomial with variable x. And so you can kind of think of this as something similar to y equals mx plus b, right? So y equals mx plus b is also a first degree polynomial, but it's also kind of the junior term for how we describe a line. So that is to say, let's just graph a line tangent to f of x equals e of x, and we'll do it at a couple points. So the first point we're going to do it at per this graph is for x equals 0. So the way that you would do that, so first identify where this is happening. So you needed to go through the point 0, f of 0, because it has to touch the graph at that point. So the line contains the point 0, f of 0. And since we know that f of x is e to the x, this is the point 0, e to the 0, which is 0, 1. And then it also has to have the slope equal to the tangent at that point. So it's going to be the slope value of f prime of 0. So we know that f prime of x is e to the x. So f prime of 0 is just e to the 0, which is 1. So now we have a point and we have a slope. So we can go ahead and put this into point slope form. So remember that point slope form. So if we have the point, say, x naught, y naught, and then we have the slope m, then point slope form is y minus y naught equals the slope m times the quantity x minus x naught. So we're going to go ahead and use this to construct our line. So for us, we have the point 0, 1, and we have the slope So then with the point 0, 1 and the slope m equals 1, what we really have is y minus 1 equals the slope times x minus 0. If we simplify this further, we just get the line y equals x plus 1. So if we go ahead and label each piece, this is y equals x plus 1, and this is f of x equals e to the x. So we can see that in general, it's not a great approximation. They're super dissimilar. But if we look closer at the graph near the point x equals 0, which is what we constructed this for, we can see that near that point, right, kind of in this little bubble here, it's a good approximation. So that's kind of the whole idea behind using polynomials to approximate elementary functions. Just another quick example of how you could do that at a different point. Again, you want to use the point. So if we're going to be at x equals 1 for this instance, you're going to use the point 1, f of 1. And you're going to have the slope equal to f prime evaluated at 1. So 1, f of 1 is 1 e to the first power, which is just 1 comma e. And then our slope equals e to the x evaluated at 1, which is just e. So now we use our point slope form. So we get y minus e equals our slope, which was also e, times x minus 1. And so if we simplify that, we just get the line equation is equal to e x. So this is y equals ex, and then this is still f of x equaling e to the x. So here's another first degree polynomial approximation for f of x, but this time we did it at the point x equals 1. So here they touch in their tangent, and you can see that there's a nice little kind of area where the line is a good approximation for the function f. So in general, we can do this for as high of degree of polynomial as we want. So we're going to go ahead and define the Taylor polynomial and the Maclaurin polynomial. So the Taylor polynomial is given here, where it's just a sum, i.e. a partial series for an nth degree polynomial of derivatives, and the number of derivations you do increases each time. You also have to divide by, like this one's really divided by 0 factorial. This one is really divided by 1 factorial. Since 0 factorial and 1 factorial are both 1, they're not written explicitly, but they are there. So notice that the denominators are 0, 1, 2, all the way up to n, and they're all factorial. And then the derivatives are really, this is the 0th derivative, which we don't write, and first derivative, then second derivative, and so on, all the way up to the nth derivative. And then just like we did with the point slope form, you have to take x minus c, the x value that you were given. If you want to do an nth Taylor polynomial centered at 0, you just call it a Maclaurin polynomial. So Maclaurin polynomials are just Taylor polynomials for when you're centered at 0. So another way of saying this is centered at 0. So that's a finite sum. However, you can look at a Taylor series and a Maclaurin series and let n go all the way up to infinity, in which case you would have the expression here given with the summation, or you can write it out with the ellipses. So those are what each of these represent. They're just the infinite form of the definition above.